Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. So we are extremely pleased of having today Güzin Bayraksan. So she's a professor and associate chair for research in the Integrated System Engineering Department at the Ohio State University, and she's also an affiliated faculty member of the Sustainability Institute at the Transactional Data Analytics Institute. Her research interests are in optimization under uncertainty, in particular stochastic programming, Monte Carlo sampling-based, and data-driven distributionally robust methods. And she applies those techniques to water resources management problems, as well as water energy infrastructure design and operation. Her research has appeared in leading journals in the field, such as Mathematical Programming, SciAm Journal on Optimization, and Operations Research. And her research has been supported by multiple grants, including funding from the National Science Foundation and the Department of Energy. She is as well the recipient of important awards, such as the NSF Career Award. And in terms of service, she is the founding editor of Optimization Under Uncertainty, which is a newly established open journal of mathematical optimization, and serves as associate professor of operations research, computational optimization and application, and IISE transactions. In the past, she has served as the chair of the Stochastic Programming Society, vice chair of the Optimization and the Uncertainty Informs Optimization Society, and to end, she has also been president of the Informs Forum on Women in Operations Research and Management Science. So we are very pleased of having you today. The floor is yours. And by the way, for the audience, please remember that you will have time for questions at the end of the presentation. But if there is a very, very urgent questions, please put it in the chat and we will read it for Güzin. Thank you very much for being here, and the floor is yours.
Thank you, Dolores, for this great introduction, and also inviting me, but more importantly, for organizing this Machine Learning Needs Mathematical Optimization online seminar series for a while now. As you say in your website and announcements, this is very important to brand operations research and its role in machine learning, AI, these up-and-coming topics. So today I will be talking about integrating stochastic optimization with machine learning through a pretty intuitive and simple actually method using regression residuals, right? Or the learning method, we use the residuals of it to create a stochastic optimization method. So this is the title I gave, but what I will be presenting is this one, and the second part of my talk, I'm going to show you a real-world data application for a very important power systems operations problem, a fundamental problem called the unit commitment problem, and see how this works with real-world data. I would like to start by thanking my co-authors and collaborators. So the first part of the talk will be a little bit more theoretical and, setting up the problem, what we are doing, and some theoretical analysis. And those are with Rohit Kannan, who is now at assistant professor at Georgia Tech, and Jim Lutke from University of Wisconsin-Madison. And the unit commitment problem is with Ogun Yurdakul, and he has been the driving force for starting that project. He's currently at Trailstone Group, maybe Argonne National Lab soon. And I also want to gratefully acknowledge the Department of Energy grants, thanking anybody who gives money. All right, let me start by introduction. All right, so on one hand, we have the data, and, from classical statistical methods to more modern machine learning tools, right? We try to use the data to make inferences, but our ultimate goal is to make decisions on, let's say, a business problem, an operational problem, engineering problem, whatever we're studying, right? And unfortunately, when we make these decisions, we have to do it under uncertainty. So what we want, which these two fields perhaps somewhat separately evolved, what we want to do is we want to go from data to decisions in a more seamless end-to-end fashion and sort of integrating them. And I'm going to talk about one way to integrate them, which is, as I said, a pretty intuitive and easy method using residuals from the learning methods, right? So that's the crux of the talk and an application. So the first part of the talk, as I said, is going to be looking at this in a more theoretical manner. So let me start with traditional stochastic optimization. So if you're a stochastic programmer in the audience, you would see this as a little bit of a different setup in terms of notation, because we are using Z as the decisions we need to make. For instance, for the unit commitment problem, right? When are we going to turn on the generators? When are we going to turn off the generators? How much energy we're going to produce? And the Y is the demand or the load, sort of the load profile that we look to schedule for the next 24 hours, next day. And we have a cost, so it's uncertain demand, and we look to minimize expected cost. So here, Y denotes the uncertain parameters. This is more like the statistical notation. We're going to use capital X, capital Y for the random vectors and random variables, and then Z is going to be the decisions, and that calligraphic C is the feasible region. All right, so obviously we cannot solve this problem. Usually we do not know the distribution of Y. Even if we assume something, that expectation is a multidimensional, very difficult thing to estimate. So a typical way is we have some data, could be independent and identically distributed, or IID for short. Or usually it's not actually in real world applications, but some observations. We collect, let's say, net load, net demand from the past, and we estimate this expectation essentially by a sample average approximation, right? So we replace this by the sample average approximation using the data, the observations that we collected. And this is a very well-studied topic with lots of theoretical results for many years. And the first one is like, if you want really deep, that's the book by Shapiro, Dancheva, and Rudzinski. And the other one is like a survey that I've written with Tito Hamamnamel. Anyway, so that's the traditional problem. What we're going to do is we're going to use covariate information, or also known as contextual information, auxiliary variables, features in machine learning, side information. There are multiple names for it. So as you can see, the difference between this problem, where we have, like, we're taking expectation with respect to, let's say, whatever the demand is. But here we have covariates, so we're going to estimate the demand for a given covariate. So maybe the temperature, maybe some other things are going to affect the demand, and we're going to utilize them to get a much better estimation. But in the end, we solve a conditional stochastic program. So stochastic optimization problem, CSO, or sometimes called contextual stochastic optimization. Both of them, luckily, have the acronym CSO. We've changed the problem setup, right, a little bit. So we're going to then directly use the learning part and then embed it into our stochastic optimization. And this is the main difference, using it conditionally for a given set of covariates. All right, and we have the same thing. Okay, let me first talk about some example applications. I've been talking a little bit about this, right? For instance, we may have renewable energy outputs, the load and the minus, if you subtract them like a net load, then, for example, if we have solar panels to produce renewable energy. And by the way, happy Earth Day today, talking about renewable energy. So we may use weather forecast, we may use temporal information like time and day and many other things to estimate the energy outputs as well as the demand. and then we need to come up with scheduling decisions. Another example is portfolio optimization, right? This is the return of the stocks that we need to estimate, but we can use many other information to estimate much better estimation of the return of the stocks by using economic indicators, company data, other indicators, and in the end, we need to make portfolio decisions. All right. But the idea is the same, that we have some form of data. Now we have both our, let's say, demand data as well as some covariates. This is historical data. We look at, for example, when the temperature was like this, it was a weekend when the wind energy was like that and the solar irradiance was like that. This is how much the electricity demand minus the renewable production was, and we have all this past data. And so what we're going to do is, in a similar fashion, we're going to form a sample average approximation of the conditional stochastic optimization problem, right? And the way we're going to do it is, we have the past data. Now we need to make decisions for the next day. So we use the current covariate, the new covariate that we have. Given the new covariate and the past data, we're going to now estimate the conditional distribution of the demand given the new covariate, right? And we're going to form a sample average approximation. So to do this, we have two components. The first one is the learning component, statistical learning, machine learning. The second one is the optimization component, where we integrate that learning model with its errors into the optimization and create a sample average approximation. All right. So the way it's going to be, as I said, it's very intuitive. So first, we take some data, right? This is past historical data, the demand, as well as the covariates. And we're going to use some learning methods, could be classical statistical methods like ordinary least squares, or more modern methods. So we're going to pass it through the learning stage. And what we're going to do is we're going to use both the prediction, right? So the prediction will give us what Y could be given the new covariate, right? So we're going to predict the distribution or some information about it. We're going to predict that. Plus, from this past data, we're going to get the residuals, the errors in the past. We're going to use them to estimate, and then we're going to get some errors of our estimation. So we're going to use, let's call them, like, for each data, right? We're going to get some residuals based on the data points. Now we're going to use both of them to create a stochastic optimization problem, solve it, and in the end, get our decisions, right? And this figure is adapted from the Sadhana, which is like a survey of this class of methods. So this is not the only way, right? As I said, I believe this is a very intuitive, very easy, very practical method that people actually have been using, and it has been suggested in the literature as well. I put some of the first papers doing this, but there was no real sort of a theoretical study of this method, residuals-based method. And so that's what we're going to do next. All right. One thing I want to mention is, why do we need the residuals? So this is from the case study that I'm going to present later, right? So if you look at this, this is our actual net load on a given day. I believe this is from some day in September 2019, right? And we did a prediction using a whole bunch of covariate information, and that's using k-nearest neighbor prediction, right? A non-parametric learning method. So, and that's like the tick one here is its prediction. So it gets the duck curve, but here it underestimates, here it overestimates what the net demand is going to be, or the net load is going to be. And this is one day, 24 hours of that day. But the little lines, I mean, the thin lines that you're seeing here are the residuals. This use, I believe, 30 or 60, data to do the training. So then these thin lines, some of them are below, some of them are above, right? So this gives the errors around that prediction, and that makes it a stochastic optimization model, because you need to consider. If you don't consider it, you're going to make errors, actually, because your estimation, unless you have perfect forecast, you're not going to get the same thing, but you need to consider the errors in the estimation. That's why we use the residuals, and that's critical. All right. So now I'm going to get into the more theoretical analysis of this and give you an idea of, first of all, the problem setup in more formal, mathematical formal way, and then some idea of the theoretical analysis. So first of all, there is a relationship between, let's say, our demand and the covariates that we have, right? So we're going to assume a form like this. So the conditional distribution of y, given the covariates, the current covariate x, is going to have this true regression function that we don't know. By the way, it doesn't have to be a linear. It could be nonlinear. It could be super complicated function. Plus, so in this work, we're going to assume additive error, right? So this is the error part. So this f star is basically the conditional expectation of y given x. It's, as I said, it's the regression function. And it could belong to some class of function. It could be infinite dimensional. It could be like if you're doing ordinary least squares, it could belong to like linear functions. This is the true one. If the true one is linear, then you can assume that. Or, you can leave it for quite general class of functions. As I said, this is the regression error, and per usual assumptions, they are independent of the covariates and mean zero, right? So this is a very common assumption. This one, we can actually relax that. So we have a version where it's heteroscedastic rather than homoscedastic, right, as in here, so that this independence assumption can be relaxed. But I'm not going to present that. It's cleaner this way, okay? So given this structure, the conditional stochastic optimization or the contextual stochastic optimization problem is this: we're minimizing conditional expectation given the new covariates little x, right? But we have, once we assume this structure between this conditional distribution of y given x, this whole thing is going to turn into basically, sorry, I don't know why, what's happening. All right. So this one is going to turn into this one, okay? Because we assume this is the true functional form of our, the relationship between y and x, okay? Of course, there are a number of things here. We don't know what this true regression function is, that true relationship is. We don't know like the distribution of the errors really. And then even if we know it, taking this expectation again is a very, very difficult problem, multidimensional for real world problems, right? So then we have the same issue. We cannot solve this. We don't know multiple things here. So given the data, and usually this is not independent and identically distribution, and some errors, right? Suppose we know the true distribution, true regression function here, then we calculate the errors. We have n of them in our data. And then this is something in between. This is a full information sample average approximation. So this one, the full information sample average approximation, assumes if I know, which normally, of course, I don't know, what the true regression function is. But if I know it, then solving this is very difficult. So this is like a regular sample average approximation if I knew it, right? So we're doing the same thing as traditional stochastic optimization. Of course, again, we cannot solve this. So what we are going to do is we're going to estimate this regression function using some learning method. And you can use whatever you want, your favorite statistical machine learning method. So this procedure is very modular, like it allows, as I said, very traditional methods to more modern methods. But if you want to push the theory, of course, you need some statistical properties of this learning to hold. But, it's very modular. You can use whatever you want. So for example, here you minimize let's say this is a square loss function, like a least squares type of estimation, right? So given the data, you have some estimate for n data points of the true regression function. Right? And it doesn't have to be in this form. You can do many other things. So one way or another, you use your favorite method to learn the f star. Now, once you learn it, then you calculate what we call empirical residuals, right? The empirical residuals is like, okay, you use this n data points, and each data point now you look at, I mean, in a simple linear regression fashion. For example, this is your linear function, this is your data, right? So the errors, the residuals are going to be how far you are away at each data point. So those are going to be the empirical residuals, right? So we calculate those. Now, in our problem setup, we have a new covariate, a brand new covariate that is, could be part of the data or a brand new sum X. Now, given the new covariate, we estimate what our demand is going to be. Plus, we basically use the empirical residuals from the training method to create scenarios around it. If you remember that KNN estimation that I showed you, your prediction might not be perfect. So when you add the residuals, you basically put in the errors and turn it into a stochastic or optimization under uncertainty, because you are taking into account the uncertainty in your estimation procedure. And so in the end, what we come up with is this method, which is what we can actually solve, right? This is a sample average approximation. This is our best estimate of, given the new covariate X, what would be Y. And then this is our empirical residuals, or ER. So that's why we call it empirical residual based sample average approximation, or ERSAA for short. All right. So as I said, this has been used actually and proposed, but it has not been fully analyzed, and that's what we're going to do next. Okay, so here is the some idea of the theoretical analysis, right? And usually one of the things is that, okay, does it have convergence properties? So if I obtain more and more data, does it go to the true problem or the optimal solution of it? Is it converged to one of the optimal solutions of the true problem that, I can't actually solve? But as I get more data, do I get closer? And what is the rate of that convergence? Do I converge to it slowly? Do I converge to it fast? Or how about finite number of samples? Can I make theoretical claims with finite number of samples? All right. So these are the things we're going to look at, starting with the asymptotic consistency, right? As I get more and more data, do I converge to the things I want to estimate? So just as a reminder, and some more notation here to make the sort of to write the results, right? So the first problem that you're seeing is the true conditional stochastic optimization problem, which is hopeless that we can solve because we don't know the true regression function. We don't know what's the distribution of that. Even if we do, we can't take this expectation. So there are multiple issues, like this is what we want to solve, but of course we cannot solve it. Now, in between this and the thing that we can solve is called the full information SAA, right? This assumes I know the regression function, but I cannot calculate the expectation, so I replace it by a sample average approximation, right? So that's why it's called full information SAA. Of course, we also cannot solve this because we don't know what this regression function is. The problem that we can solve is that given the data, we first estimate the regression function, and then we also estimate the residuals by using empirical residuals, and then also we have this approximation of the sample average approximation, right? SAA. So the last problem is what we can actually solve, but the first problem is what we want to solve, all right? And the analysis is that, okay, so if this is the optimal solution, will it converge to this optimal value, will it converge to that as I collect more and more data as n goes to infinity, let's say, right? And the analysis of this is going to work by basically looking at the difference between the first one and the second one, and then the second one and the third one, right? So we're going to close the gap that way. And if we have good properties of our sample average approximation, if we know the true thing, and on top of it, we need to have good properties of the learning method, then we are good for a class of problems, right? So we also need properties on the stochastic optimization problem as well, because it won't work for all of them. All right. So in terms of notation, again, this G is the true function. Gn star is the using n samples, but using the true regression functions f star. And then if you see the superscript ER, that's the empirical residual one. And Vn hat E, this one is the optimal value of the problem we can solve. This is the true optimal value. All right. And even more notation, this is the set of optimal solutions to the true problem. And then this is an optimal solution and the set of optimal solutions to the empirical residual problem, right? Again, we would like to sort of like, what is the relationship between these two? If I solve the empirical residual one, do I get a subset of the optimal solutions at what sample size, or as I increase the sample size, and so on and so forth? Okay. So the assumptions are going to be threefold. One is on the problem structure. So if you have a not well-posed problem, you lose convergence properties. So one of the things is that the cost function, for example, right, satisfies some kind of smoothness or Lipschitz condition on the demand, right, for every given decision that we can make, like the unit commitment decisions, when to turn on and turn off the generators. On the demand or net load, we need a Lipschitz condition. So if this is satisfied, for example, and can be satisfied by two-stage stochastic linear programs or two-stage mixed integer with continuous recourse, for example, right, we're good to go. This assumption can also be relaxed to local Lipschitz continuity, but it needs that the relaxed assumption will need more assumptions on the regression function. All right. So once we have the problem correct, now we're going to look at is our sample average approximation behaving correctly? So if I know the true regression function, so I need conditions, and I'm not writing those conditions, but I'm giving you the idea of this, right? So the full information sample average approximation should behave nicely. If I knew the regression function, it needs to converge in probability here to the true expected conditional expectation, right? And uniformly on my decision set. So this has been, analyzed. There's lots of things on this, many different conditions that stipulate this from classical SAA analysis, right? But this is kind of a requirement. When I know the things, if it doesn't work, then there's no hope, right? And then, of course, the third thing is to have consistency, like in the limit, we need the learning procedure to also satisfy good properties, right? So under, let's say, appropriate assumptions for ordinary least squares, it doesn't have to be IID, maybe alpha mixing, or other types of non-IID sampling. You know that your ordinary least squares for a linear function will converge, right, to the true regression function. And we also, that's pointwise for every covariate X, we also look at the mean squared estimation error consistency. So the mean squared error goes to 0 in probability here. So these things have been studied in statistics, machine learning literature, right? For a variety of different learning methods. These have been established under different conditions. Okay. So under those assumptions, then basically the optimal values will converge. And this says the distance between the set of optimal solutions of my empirical residual problem and the true set of optimal solutions, the distance between them will go to 0. So basically, if I solve the empirical residual and I keep increasing my sample size, I'm going to get, all of these will be sort of, there's some that's going to be essentially in the limit, one of the optimal solutions. Okay. And then similar results for the objective function value. And so it kind of makes sense. We can also look at the rates of convergence by strengthening these assumptions. Let's see, I have something in the chat. What type of distance? It's, let's see. It's between two sets. I believe Hausdorff will do. Oh, I think, yeah. Yeah. So let's see if I can go. Is there another thing? Okay, get it. Thanks. Yeah, no problem. And now, so we can do basically the rate of convergence, right, by strengthening the assumption. So the rate of convergence basically said, okay, I get in the limit, I get the result, but how fast do I go there? And I would rather go there faster than not, right? Than slower, obviously. So then, again, people have studied these things. Now what we're going to do is on the regression step, we need some kind of rate of convergence. So there is typically some constant here, right? And 1 is better. The higher is better. Lower is worse. And so we have like the pointwise, it's going to converge, but the rate of it is, this is big O in probability, if you're familiar with that notation, in sort of, let's say, 1 over n or 1 over n to the power alpha, right? And the same thing for the mean squared estimation error. And people have studied these things. So for example, for parametric regression models, if you assume the true regression function, the true relationship is linear, and you do use like a least squares or lasso, like with a linear estimation function, then things are looking good, right? This is what we want. On the other hand, many problems do not have this linearity. So you go to like non-parametric models, estimation learning, which can actually, cover a much wider range of problems. And under appropriate conditions for those, this rate is also satisfied, but there is sort of this dimension of the covariate x. So as the dimension of the covariate x increases, they converge slower and slower. So there's a curse of dimensionality in these non-parametric methods. On one hand, they allow a richer class of regressions, right? They can estimate things better, especially when there's nonlinearities. On the other hand, you pay a little price by converging, but converging slower, especially as the dimension gets larger and larger, okay? And then you can basically show a center limit theorem type of result that the optimal value of the empirical residual problem will converge to the true optimal, this kind of a rate. And this hides, by the way, a bunch of other terms. So just writing in terms of sample size here. So you have the alpha over 2. Okay, so there's some loss there. If you start with alpha, you're going to do alpha over 2. And then if you're using non-parametric ones, you're going to lose a little bit more as the dimension of the covariate x increases. All right. We can also look at finite samples. So these are all like, again, in the limit as I'm taking, sample sizes to infinity, which is not what happens in real life. So for finite sample guarantees, if you're familiar with this type of results from the literature or like sample average approximation literature, right? So there is say kappa, an optimality gap. So what we're looking, where does that kappa come into play is this one. Set of kappa optimal solutions to the true problem at the new covariate x. Okay, so I'm not looking into converging to the optimal solution, but kappa optimal solution. So I allow near optimality. Okay, and then this is what it is before. This is the set of solutions to the empirical residual problem with n sample size. All right, again at the new covariate value x. So now we can ask this question. Suppose I use a sample size of n, let's say 1,000, 100, whatever. What is the probability that my optimal solution of the problem I can solve, which is the empirical residual problem, right? Empirical residual-based SAA problem, optimal solutions of it, what is the probability there are going to be kappa optimal solutions to the true problem? Again, asking for optimality for finite sample size is too much. So we go kappa optimal, so near optimal. And can I control that probability and say, oh, okay, what is the sample size needed? So at least 90% of the time, I'll get a kappa optimal solution, right? This is like a finite sample guarantee. So we do this again in 2 steps. One is the sort of classical sample average approximation analysis. I'm not going to bore you with this. Whenever you see O1, that means some kind of constant. So these are like, but it depends on what kappa is, what this probability level is. So if you want 95% versus 90%, like you're gonna pay a price. You need to increase your sample size. If you want kappa optimal, like let's say within 1% optimality or 10% optimality, right? So 1%, you're gonna need to increase your sample size, clearly. It also shows up here, right? So this is a classical result. So I'm gonna call this sample size classical. By the way, these are theoretical. They're very conservative in real life, and there are, many constants. You don't need to worry, but it gives you an indication of how things work, right? So what we're going to do is we're going to look at, so every time you're going to see that classical, plus there's going to be additional sample size requirements. So the first one is the full information SAA to converge to the true problem. And the second part comes from the learning, because now you're adding the learning step. You're incorporating the learning into the stochastic optimization. So you have to kind of pay a price for the learning to also get good. So if the true regression function is linear and you use correct model for it, the ubiquitous ordinary least squares, right? The sample size is going to increase sort of linearly with the dimension of the covariates. If, on the other hand, it is S-sparse linear, so you have hundreds of them, but only 3 of them are important, right? That's S is like 3. So it's sparse, like you put in a lot of covariates, but only 3 of them are the actual ones that matter. And you use Lassa to capture this, which is a regularized version of the ordinary least squares, then it gets significantly better, right? Then you shrink this linear dependency on the dimension to logarithmically. So it's actually like requires a lot less sample size because it's sparse. And you capture that sparsity by using lasso. On the other hand, now you go to nonlinear regression function, nonlinear, but here it's a nice nonlinear with Lipschitz continuity, and you use k nearest neighbor regression. So if you use ordinary least squares, then that's a problem. But if you use k nearest neighbor, where you need to increase your k according to that, right, how many nearest neighbors you use, then there's this curse of dimensionality that comes into play. So this is your dimension of, let's say, the demand to the power dimension of the covariates, right? You need a lot more sample size. And we knew this beforehand because the convergence of these non-parametric models that allow much richer classes of regression functions, they pay a price by converging slowly. And to get the same level of finite sample guarantee, you pay a price, right? So there's dimension here, there's to the power dx, and so it's much worse than the parametric ones like ordinary least squares or with the linear or sparse structures. Okay, and so this is summarizing all of that. Okay, so I've already said all of these. Now let me move on to the unit commitment in electrical power systems. This is the one with my collaborator, Güzin Yurdakul. And we have used real world data. So this is a fundamental problem in power systems operation. So I'm not an expert in this, but there are many papers written about unit commitment, different formulations, different things. Right? It's basically what it does is like given some generators to generate electricity, when should they be started, when they should be stopped, how much they should generate electricity to meet the demand, right? Minus the renewable energy that we get at a minimum cost and distributed also sometimes. So there are constraints like minimum uptime, downtime. So if you turn on a generator, you cannot immediately turn it off. You need to have it, on for at least a minimum amount of time for it to, work. Same thing when you turn it off, you cannot immediately turn it back up. These are physical constraints that you have to obey. And again, ramp up, ramp down is like if you start producing energy with a generator, you cannot go from 0 to 100, right? Even with the cars, etc., like you just cannot go 0 to 60 something, whatever seconds, right? And there's some ramp up constraints. You can only do it at a particular rate. The same for coming down. And then transmission network, power balance constraints and whatnot, right? So one thing that has been happening that is affecting this type of, important power systems operations problems is that the renewable energy, the portion of renewable energy into the system is increasing a lot. And it's also, by policies and other things, like it's expected to increase more. So this is, by the way, from the US Energy Information Administration from 1950 to 2022. And you can see like this is petroleum and other like old stuff. And this is the renewables, the green one, like the share of it is increasing over time. And our energy demand is increasing as well, as you can see. And within the renewables, so same time frame, 1950s to 2022, this is hydroelectric, right? And then this green one that has been increasing in the last 10 years or so is wind. And this one is solar, right? So you can see the wind and solar proportion is like increasing, and it's also expected to increase even more. What is issue here is that increased renewable energy, especially wind and solar, etc. Hydro is more, even hydro has its like, as the climate changes, if there's less rain, you cannot store the energy. There's issues with that, huge issues if your reservoir levels go down. But in the wind and solar, there's a daily uncertainty, right? It's not like coal-powered or nuclear energy generation. It's not as smooth. There's temporal effects and other things. So there's a lot more uncertainty in the system now. So we need to use stochastic optimization methods, optimization under uncertainty. And on top of it, right, as I said, this is great for, I said today happens to be the Earth Day, so love it for our planet. But again, we have to consider this. And on top of it, we need to leverage the covariate and contextual information, right, to make better decisions. So we are using in our study net load. This is basically, think of it like the total demand minus what is produced by the renewables, especially wind and solar, to basically that will lower the net demand, right, by renewable energy production. Okay, so to do this, for example, we've applied it to California, ISO, Independent System Operator, and New York, but I'm only going to show California. So what kind of covariates did we use? So for example, we have used climate related, like temperature, right? If there's hot temperatures, people run the AC. Vice versa, maybe the heat, whichever one uses electricity, right? So in densely populated areas in California, we use 24 lagged measurements of temperature. And then when the areas where there is wind energy production, we looked at the wind speed measurements from those locations. When there's solar energy production, those areas, we looked at the solar irradiance. We also used, so these are renewable energy generation. And then we looked at, for example, temporal time-based. So for cyclical, for seasonality effects, we look at month of the year, which is represented using sine cosine so that the cyclical pattern is there, right? And then also, is it a weekday? Is it a weekend? Or is it a public holiday? So these things have different energy load, electricity load profiles. So we use this as well to figure out what the demand is going to be. And we used one encoding for those, if you're familiar with that. Right, so it's like 0101, like something along those lines, weekday, weekend, or public holiday. And in addition to all of these, we used past net load moving averages. So for example, if we're going to predict tomorrow's electricity demand, we look at, for example, 1 day ahead. What was the electricity demand 24 like hours, the past day essentially, right? What was it? And we also look at it weekly and monthly to get, nearby, and then, maybe go through that year if there's some increase of demand or some changes in demand in that year, and so on and so forth, or the last couple of years. Okay, so overall, I believe like this is going to be 440 covariates, right? Okay, so using this, we looked at a number of regression or learning setups. So these ones are ordinarily square. So these are the parametric models with assuming some kind of linearity, right? So ordinarily square is the classical and most widely used statistical method. And then it's regularization. So ridge regression is one type of regularization. Lasso also like induces sparsity. They are related in the same class of things. And then we also looked at non-parametric, somewhat more, I want to say modern, but they're 20 years something, random forest, k-nearest neighbors. And for these, we also do hyperparameter tuning. So k-nearest neighbor, how many nearest neighbors you're going to use. So how do we determine k here? We do on a separate data set, independent data set. We look at like different values and pick the best out of sample performance. Random forest has many parameters to tune. We tuned only 3 of them, like how many trees we have in the forest is one of them. And then lasso, etc., have the regularization term that needs to be tuned. We did the same thing. Okay. So once we fixed those, then we did our analysis. All right. And so we are going to look at our empirical residual-based SAA, contextual or conditional stochastic optimization model, but we consider the following benchmarks here. So the first one is a point forecast. This is not a stochastic model, right? There's no expectation here. This is a deterministic model where, okay, I forecast my demand to be this in the next 24 hours. I solve an optimization problem, no uncertainty. My forecast is the ground truth, right? I assume that and I solve this. So obviously, if your estimation is not good, you're going to make a lot of errors. Another one is the naive stochastic unit commitment. This one uses no covariate information. So you have net load demand without the covariate. So you don't care if the solar irradiance was this or that. You just plug in all your data and try to do this. Of course, you're not leveraging this information, so you would expect it doesn't work well. Maybe if you have a lot of data, then it may. So, and the other one is ideal unit commitment. This assumes perfect foresight. So what we do is we train it on, let's say, using 60 data points. We get the learning, the how much demand is going to be next day given our covariates, plus the residuals. And then we implement it on a separate, let's say 1 month or 4 months throughout like each day. And then we check how it performed, right? Our method. But this perfect foresight, basically on each of those days that we evaluated, if I knew exactly what was going to happen tomorrow, this is the best one. Again, this is a deterministic optimization problem. It assumes, right? I know everything that's going to happen. I'm an oracle. I can see the future. And so it's a lower bound. Basically, it gives us a lower bound, but it's not attainable in real life because we don't know what's going to happen tomorrow. All right, so those are the 3 things. So if you see PF, that's the point forecast. Naive is going to be this. Ideal is going to be denoted by that. All right, so here are some results. I don't know if you can see. So this looks at ordinary least squares, KNN, and the lasso version, the regularized version of ordinary least squares. So the 3 of them. So we have more methods, as I said, but this is just to show you something. I don't know if you can see. This is OLS and KNN. This is OLS and looking at lasso. And then this one is sort of all of the contextual or the conditional stochastic optimization. Again, it's very hard to see, I think, but this one over here, This purple one is IUC. So this is the train, by the way, the x-axis is the training set size. So as we increase the training, we get them, they're going to get better. The models all get better. And this is the total cost, out of sample cost, when we evaluate how it does outside of the training, right? So we start the training with 7 days minimum, 14 days, etc., up to 1 year. And the lower here is better, right? So if you look at here, the Canon works really well. I mean, it's hard to see, but like contextual one goes here and is like very near the ideal one, right? The lowest it can get. And then if you use the point forecast of it, the point forecast of Canon is still doing well, but it's above. Ordinary least squares, on the other hand, is doing terribly, especially with small training data set. And we're going to discuss that. So we use lasso to see if we can make it better. And you can see it actually shrinks it from here to here. But even with those with small sample size, they're not doing as well as their point forecast. So these dashed ones are the point forecast. But then if you increase the sample size, let's say about 60 or something, the training sample size, then, you know, or yeah, they get better and then they converge also to the ideal one. Right? But they, in this case, OLS actually seems to converge a lot slower. And Canon in this case works really, really well, as you know, it's the repeat of that thing with all of them together. Like it's just even with very small sample size. So what's happening here when we look at it, here's what happens. This is a particular day in September 2019. This is the actual net load, all the same in 3 graphs, except I believe the x-axis here is different. So this is the 24 hours of that day. And then this is the net load. This is the famous duck curve, right? So if you use ordinary least squares prediction, first of all, it underestimates the demand by quite a bit. All right. Second, so this is the estimation, but this graph also includes the residuals from the training set. So the residuals, I mean, they're plotted there, but you cannot even see it because they're so close to 0. This is because OLS it's actually overfit in the training. It's like overdoing it, which means it's actually doing much worse on the out of sample. Take a look at KNN, on the other hand. First of all, its estimation is significantly closer and better to the actual one because it allows nonlinearities. And on top of it, the small lines that you see, I don't know if you can see them, like these thin lines, are the residuals. So then there's some above, some below. I've shown it. This is the same graph I shown at the beginning of my talk, right? If you consider all of them, it also considers the errors really well. So because of overfitting, OLS is terrible. Lasso corrects OLS not as well as Canon. In large training sample sizes, Lasso is also very good. But you can see it's closer, following closer to the actual load, and the residuals are not 0, right? So it gets much better results. So overfitting is a killer here. It shoots itself double. The prediction is bad, and on top of it, the residuals, because in sample was so good estimation, overfitted, that it thinks the residuals are 0 and it cannot capture the errors correctly as well. So how do we mitigate this? One of the ideas obviously is well known. You can use lasso to mitigate the overfitting of OLS. We tried different things. So if you have a lot of data, why don't we do the regression on one data set and on a separate one of the same training size, we get the residuals. This way, like it overfit here, but the errors here are going to be much larger. And a second one is we have, remember, 440 covariates. So the more you add, I mean, regression, the more variables you add, the more it's going to fit. It thinks it's doing a good job, but it's not, right? It's not a better model, but the in-sample like error is small. So a good feature selection can actually help with this as well. So we followed this procedure, which is written here. And in the end, we basically look at mutual information score and some other things. And then so we narrow down this to the top 25 covariates. So let's see how they perform. Okay, I'm running out of time, but this is going to be, all right, so the basis is our methods that I showed, and this has more. So we've looked at ordinary least squares, lasso, KNN. This also includes random forest and ridge regression. These are all the contextual ones. This is the ideal one, the best you can do. This is average with a training sample size of 120 and an average of maybe 4 months of evaluation, total cost. We also have standard deviations, but just to show it, I removed that. And these are the point forecast results, right? So as we know from previous, KNN works like really, really well. Lasso also, now the training sample size is large, is also doing very well. And the random forest, again, captures the nonlinearities like KNN, so it works well. OLS, I mean, you can see the total cost here, and the ridge basically follows ordinary least square. They're doing terrible, right? Even like ordinary least squares is doing worse than the point forecast, even with a relatively large, because of this overfitting. Now let's do the second method. We're gonna now take the, we're gonna fit in one training data and use the residuals from the other to remove this overfitting. And you can see a huge drop in both the OLS and ridge out of sample costs. But it's still not enough, right? I mean, it's doing better somewhat, but I mean, KNN is doing great. Ridge regression, random forest, the non-parametric methods are doing very well. They also shrank a little bit, right? So it also helped. Doing this helped them, but it's not necessary. Let's see, I have a question in the chat. Cost equals energy consumption. Cost equals like load curtailment. So first of all, they're operational costs. And then there is a very high penalty of load. If we cannot meet the demand, there is a high penalty. Yeah, thank you for that question. Yeah. So operational cost plus sort of a penalty cost. And then, so the next method is the feature selection that I just mentioned. So let me go to that result. Okay, so the feature selection, you can see huge improvement for ordinary least squares, and I mean, ridge again follows it. So much so that, I mean, it also helped if you look at KNN, if you look at lasso, it helps across the board. And not only that, take a look at the point forecast. They have also shrunk a lot, right? So the feature selection helps across the board. And specifically, it seems to help with a large enough sample size, the overfitting issues of ordinary least squares and ridge, but it helps everything mainly, right? So this is another sort of, you know, people who do statistics, etc., know these things, but sometimes this is overlooked. And in this application, especially, this made a big difference in all of the methods, and especially for these parametric ones that did not perform well. Okay, so wrapping it all up, right? Empirical based residual method to combine in a sort of a linear fashion, but a nice, easy, intuitive fashion, especially for practitioners. Use your favorite machine learning. Use both the estimation and the residuals and create a optimization under uncertainty, because you need to consider the uncertainty of your forecast. If not, you're not going to do well, right? So point forecast is usually worse, except for those ordinary least squares overfitting one. It's pretty much worse, right? And it works with real world data. It looks like there's some nonlinear relationship there, but even with linear, when we do feature selection, it seems to work well. And then I didn't show the results, but naive SAA, when we use without covariate, is like much worse, especially in lower sample training sets. I didn't show it, as I said, it's really, really much worse. And then, so there's benefit in using the covariate. I mean, that's also like, makes sense, right? If you know what it's going to be a sunny day and a cool day, you can actually produce a lot of solar energy, and windy or something, right? So, I mean, use that information, that weather forecast, to your advantage. And then overfitting is a big issue for this residual-based method. And it looks like feature selection is beneficial across the board for this method. Okay. And so basically it's a modular approach and seems to work with real world data. That was great to see. And then I'm working on a number of different extensions of it. I said earlier, like handling heteroscedasticity where the errors depend on the covariate, right? So if you have a sunny day or a cold day or a hot day, you know, how much error you make might be different, right? Or if it's some public holiday, it's harder to estimate, you have few of those. So the errors could depend on that, and so that can be handled. Already there's a distributionally robust version already published in mathematical programming. I'm also working on currently, when you bring in decision-dependent uncertainty, then the models get more complicated, but now your covariates, part of your covariates become the decision. So for example, we're also looking into applying it to electric vehicle charging station problem. So if you open more charging stations, electric vehicle charging stations, you increase the demand of electric vehicles in that area because people see that they get reduced range anxiety. So, and capturing this decision dependency with real world data and regression is another, you know, ball game. And then there's theoretical results for that. So we are almost done. So coming soon to an archive maybe near you. Also looking at streaming data as you collect, you know, a lot of data coming in. Can you do some quick things? Multi-stage extensions, I believe Rohit and Jim have been looking into that. And there are many more, of course. And so I thank you for your attention. The papers and the preprints are available. First one, the theoretical one on archive, and the second one is already on early access paper in IEEE transactions on power systems. So thank you very much, and I'll be happy to answer any questions you have.
Thank you very much for the great presentation. So to the audience, we should be giving you in a second access to the microphone and the camera, and you should be able to ask questions. So I see that Emmanuel has a question. So Emmanuel, if everything is okay, you have the rights to the, yeah.
Thank you, it works. Thank you very much. Thank you for the great talk, Güzin. I have a question related to my question in the chat. So you
could you
reported
remind me? I'm sorry.
cost is energy consumption, and you kindly pointed out that there's a huge penalty for not satisfying energy demands, right?
Yes.
And
correct.
the curves you showed us are predictions for energy demand.
Yes, net demand.
Net demand, yes, which is
Yes.
the quantity which would incur a huge penalty if you underestimate it, and a small penalty, if at all, or a small cost contribution if you overestimate.
I see.
Is
Yes.
correct?
Yes.
And
Good
looking
point.
at your curves, I would think that OLS is would incur less cost anyhow, because no, wait a minute, KNN would incur lower cost because of being too conservative.
Overestimate. I mean, but that's one example, right? That's just one day of
yeah,
the
but
thing.
it would even strengthen the argument of your method, because despite of this higher total cost, perhaps by just this asymmetry in penalty, you still get better results with your approach, which I found very impressive. But my question was just to understand whether this was the correct interpretation.
Yes, I think so. Again, thank you for bringing up this very nice, approach. Like, because as I said, I'm not an expert in this, but this is a very good point. But I also see some general things. So for this problem, absolutely. But I do think like not, overfitting and not being able to get those residuals correctly is, I think, a big problem in even other problems, like even underestimate, overestimate, right? So you can also have other costs, like you can give cost to over and under, and it will again be a big cost, and it will cost the system for sure, even if you have that. Yeah. Thank you for this insightful.
No, thank you. But as you pointed out, the costs are different costs, basically, different type of cost.
There's also operational costs, so there's other costs involved in this. Yes.
Exactly. Sure.
So it also includes those as well.
Thank you.
Thank you very much, Manuel, for the question. Do we have other questions from the audience? So Güzin, just for checking, your feature selection procedure was, say, prior to building all the models, right? So when
Yes.
you had at the very end, that column.
Let me show you this one. Yeah.
Yeah. So this selection was made in advance.
Yes.
Okay. Quite
Yeah, this
impressive.
was using
Quite
the
impressive.
data,
Yeah.
the training data. We do the feature selection and then apply the empirical residuals, etc. All of those afterwards.
It's
And
quite.
it did make a big difference. Yeah,
Quite
across the board.
impressive. Quite
Yeah.
impressive. Thank you. Well, if there are no more questions from the audience, we would like to thank you. Oh, yes, there is a
There's
question
something in the
coming.
chat.
So, Belen, I think you should be able to ask the question yourself.
Yeah, no, I can see it as well. If she wants to ask it, of course. Helen?
I maybe, not sure if you mentioned it, but I was wondering if kind of like you have used any information on the cost for that feature selection.
No, so I don't think so. At least Ogun, correct me. Ogun is here, maybe. I think I have seen him. I don't know if he had to leave, but correct me if I'm saying it wrong, Ogun. But no. So we typically keep in this work at least. Another good point. So this is, I think, should be examined more for future work. So I completely agree with you, Belan. So this is keeping the machine learning, whatever, this part separate than optimization so far, except for the using the prediction and the residuals, right? So one can actually consider what you suggest is to tie it more with the ultimate cost, etc., and then do this, for example, feature selection and other things, considering the cost of the system. So that would be a future work. And there are also methods of this kind of integrating or machine learning. So basically they learn for the optimization. And under some problems, this could be a very good thing. So yeah, but we didn't do that. No, this is keeping.
That's interesting.
Yeah, before.
Also with maybe not so much with the cost, but also with the decision. So it's kind of like, what are the features that kind of like help more in or make a difference in the decisions that need to be made after?
Yeah, so that's a different kind of integration of machine learning and optimization. People have been working on that, and that usually results in more difficult optimization problems to solve because you have to consider, how to learn with the decisions embedded and things like that. And in some cases, as I said, it can work better, but it's more complicated, and the optimization model gets usually more difficult. And then there are now new papers that show under certain conditions, this sequential method is better. Under other conditions like this, the one that you suggest could be better.
One thing is kind of like what you're talking about, which is very complex. It's kind of like really tidying up everything. But here we're talking only about feature selection. So if you kind of like do kind of like some, something that takes into account the feature, so take, for example, for each example, you just run the optimization model, get the optimal solution, and then use that information for just the feature selection. Of course, if you want to use the integrated, it's more complex, and it's those words that you were mentioning, which are quite more complex. But do you know if that has been tried to kind of like just in one single space, or single part of the whole process, which is feature selection, to take that into account and then kind of like see how maybe integrated into your whole solution or something, if it works well?
I know when people are learning, so for example, random forest, something, card, like they have looked into what we need to learn to make the optimization better. I don't know specifically for feature selection. There may be, I'm not aware of it. But people have looked at the learning and modifying it for the optimization. But don't know specifically, for future selection. Again, I don't want to say there's none, but I'm not aware of it. But very good point, I think. This is definitely something to look further, especially given that how well it worked across the board, and especially the problematic ones. So I think this could make it even stronger and better. Thank you so much, Ben.
Thanks to you. Very, very interesting.
Appreciate it. Okay, I see another question in the chat. Should I read it or?
Would you like to ask the question yourself?
Yeah. So, hello, can you hear me?
Yes, we can hear you.
Yeah, so yeah, just a clarification, maybe very fast. In the beginning of the presentation, there was a picture of prediction. They had prediction for the code using KNN, and which you also showed like toward the end of the presentation. So there, of course, you are predicting load using different covariates, right? So, and you mentioned like temperature is one of the covariates for those prediction, right? So, but if you do day-ahead prediction, 24 hours ago, you are making prediction for the load. In 24 hours ago, you may not know also the temperature exactly.
Oh, no, of course, you're not using the temperature at that point, right? You don't know that. You use the temperature sort of beforehand and nearby or something like that. No. Or a weather forecast, something, Of course, you're not using you cannot use something you don't know as a covariate.
So you're using the temperature of
previous temperature or a weather forecast. Like I had another one where we used the weather forecast. So there's a current forecast. And again, forecasts have errors. For example, I have used that in some study or then, past temperature here. Yeah.
So then, like as you said, like in the prediction, we may have error, right? So in the KNN prediction, and those error also involves the error in those covariate prediction. Is that correct interpretation? Error in the prediction of the load. Error in the prediction of the load also involves error in the
so this one uses that's another work. This one uses past data. So that was another thing, like uses weather forecast.
Okay.
Yeah. So, but but in either case, yes. So even the weather forecast has its own, like it's a prediction. You are right in that case, but you're not using the unknown data.
Okay.
Obviously. Yeah.
Thank you.
Thank you.
Okay. Are there any more questions from the audience? Well, if not, again, we would like to thank your time and for sharing your expertise with us in our online seminar series. And for the audience, please note that next week we have a young online seminar series session, which is actually organized together with the Euroforum Wisdom. So it's going to be an exciting session, and we hope to see you there. Thank you very much to all of you.